Okay, so all the way from QCon, but actually from Linz in Austria, who works for Roxit. This is Alois. Thank you.
I just mentioned there is something with giving this talk about alerting systems. Every time I give this talk, either my computer breaks down or anything else breaks in. Today, PowerPoint broke down. So there is some bad karma to this talk, but I still think it's an important thing to talk about. So first, I'll start with what I'm not talking about. Like things like broken cables, or things like this, like a data center fire. That's not what the alerting system for. There are other tools that can better serve this purpose. But there are more everyday things that we want to be alerted about when stuff actually breaks. Things like you have a new deployment going into production. You have increased load. You have to change usage pattern. So typical questions that you might want to actually alert on are things like this. You typically have an error rate of 3% at 10,000 transactions per minute. During the night, we now have 5 errors at 100 requests. Is it not normal, or is it abnormal? If you want to wake somebody up, I mean, the error rate is obviously higher when you have less requests, but is it not normal, or is it abnormal behavior? Who thinks this is totally normal? And you would be fine if you have to walk into the CEO's office the next day if something broke down. You say, I'm not alerting on this. Or another example, your typical response time has always been around 300 milliseconds. And now we see response times up to 600 milliseconds. Should we alert? Who would alert? Who would not alert? Who would not? Well, things get me out of here. I don't want to do this talk anymore. It's getting too complicated. Okay, so the basic thing we are facing as we are all engineers and not mathematicians. We are very good at fixing things, but as a matter of fact, we're not as good at figuring out whether something is actually broken or not. Give us a problem, give us enough Diet Coke or Coke and pizza, and we're going to fix it. But deliberately knowing whether something is broken, especially when the system gets reasonably large, is a completely different beast. And that's what we're struggling with more or less on a daily basis. So how can we get better? The answer is it's all about statistics. And yeah, I think, oh my god, it's 7 p.m. and this guy starts to talk about statistics. Yes. So what is statistics? My definition of statistics is about objectively lying to yourself in a meaningful way. What do I mean by this? It's always about lying because you never look at the full truth. You have to condense your data down, and you have to condense it down in a way where you strip out certain pieces of your data, but the result should still lead you to the right conclusions. So, how do you actually design an incident? It's actually pretty simple if you look at it in theory. This is our baseline, this is our metric, and once the metric crosses that line, we alert. So why do we actually spend 20 minutes talking about this? So, which metric do we pick? How do we actually calculate this value here? How do we get the baseline? And how do we define that this actually happens? So there's a couple of key questions that we have to answer first that look easy, but once you look at them into more detail, you will realize that there is some more to it to actually do what. Which metrics do we pick? Basically, there's 3 different types of metrics. Capacity metrics, that define how much of a resource is used. CPU, memory, network, these kinds of things. There are discrete metrics, which are countable things, like users and errors. They're pretty easy to handle. So for a certain time period, they're always concrete metrics, like how many users did you have in the last hour? That's pretty easy to say. 100,000, whatever. And there are continuous metrics. They're defined by a range of values, like response time. You don't have 200 millisecond response time. At any given point in time, you always have a range between, say, 100 and 500, 100 and 800, 50 and 1,000. No matter how small you make your sample size, you always have a range of values. So for capacity metrics, I actually don't like to alert them. Capacity metrics are good for what they said. They are good for capacity planning, but they're not good for production alerting. So how many of you guys alert on CPU usage or memory usage of the machines? Great. Okay. And there might be good reasons for it, but not a lot. Generally some examples, like I frequently cover people that alert on connection tools. So once my connection tool is fully used, I'm going to raise an alert. Better use actually connection acquisition time. Your connection tool is there to be used. That's why you have to find the connection tool. If it however takes long to acquire those connections, that's when you have a problem. But suddenly we switch from this discrete metrics to a continuous metric. So it tells you that actually who wanted the connection didn't get it in time. Same on CPU usage. Old one, instead of CPU usage, combined CPU usage with load average. Again, tells you when somebody requested resources, they actually got them. So once you start alerting on capacity metrics, you usually combine them with something else. It's not about the capacity per se, but what was the effect of not getting that resource. Yeah, or even better, you correlate the CPU usage to your response time on the same machine, then you know whether there was really any actual impact. Discrete metrics I won't cover today. They are pretty easy to track and analyze, but now continuous metrics. Unfortunately, continuous metrics require really some extra work and are not that easy to track. This is what we think a metric would look like. Or what we want to see in the chart. We want to see this one chart that says like our, whatever this is, response time is 42 milliseconds. That's what this metric looks like. What we see here is the distribution all over time. This is not a single number, it's always a distribution. And my question would be now, when in this chart do you alert? I've given you all the data, it should be right. Very easy, right? I mean, so, just see what we do with the data. I thought about objectively lying to yourself. Let's lie this up to ourselves with using the average. Let's take the average response time in here. And that's what the average would look like. You see it kind of goes well with the metrics. Here they go up, and it actually does not look too bad. This is what the median looks like. So, quite a difference here, right? Okay, so first of all, we have to decide which metric we want to use, which aggregation we want to use. Okay, now we have that metric. Next question is, how do we get a baseline? First thing, a baseline is not a number. Baselines are not like a usual threshold. Once you go over it, you're violating your response time. Baseline is actually a range of values combined with a probability. We have seen a range of values before. If you get another range of values, how likely is it that this value is going to change that way? And the easiest means of distribution is obviously the normal distribution, where we have a mean response time of 500 milliseconds and a standard deviation of 100 milliseconds. What this actually means is that 68% of our response times are within 400 and 600 milliseconds, 95% between 300 and 700, and 99% between 200 and 800 milliseconds. That's what, for example, standard deviation-based alerting means. It gives us a probability how much of our values we get within a certain range. Actually, this can unfortunately really go wrong. Look at this here. In this case, this is a standard distribution alerting approach. The normal response time is about 67 milliseconds, but the two standard deviations are about 4 seconds, and there's some additional leverage added in there. And in this case, the alerting system thinks at 4 or 7 seconds I should actually be alerting if my response times went up from initially 36 milliseconds. I think you should, but that might be a bit late. Finally, this post was about, you see, like the baseline response time is 140 milliseconds, and the baseline standard deviation is about 1 second. So you actually have negative response times. This is a very well-performing system. What this means is, that's one of the things I remember from statistics class. If your underlying distribution model is wrong, any assumption you make on top of it is wrong. This data is not normal distributed. And the result is it would alert way too late in here. Finally, this comes from a blog that's named Well Alert, so I can monitoring solutions need to become better. So, how does this lead to false alerts? To give you an example here. So here we set a very aggressive baseline based on the average again. What this means, we alert actually quite often, too often because we don't have alert here. If we set a rather moderate baseline, we're not alerting at all. So depending on how we take these thresholds into account, we either get many false alerts or we don't get any alerts at all. That's the two things that usually can go wrong if you use the wrong underlying distribution model. In the case we've seen before, this actually happened. So the key in really alerting well is we have to find the right distribution model. If we understand how our data is distributed, we have the probability in which range we'll have a response time. In an ideal world, if it would be normally distributed, it would say, okay, 90% of the values should be within this range. If they're in there, we're all fine. The problem is finding this distribution model is actually really hard, because your distribution of response times might look like this, it might look like this, or it might just look completely different, and you never really know. You might look at your data, but even if you see the chart, it might not tell you which distribution model is underlying. And in this case, it's even most likely multimodal distribution, so there's two levels on top of each other. So how can we actually solve this problem? The good thing is we don't even have to solve this problem. Let's just look at normal distribution again. What does normal distribution actually tell us? Except being that data is normally distributed. 50% are slower than the mean, which we call the median. And 97.6% are slower than the median plus 2 times the standard deviation, which coming back is the 97th percentile. So if you ever wondered why those people say, yeah, the 97th percentile is kind of good for measuring response time, the kind of good comes from here. That's what standard deviation-based alerting usually fits into, so once you go above the 97th percentile. The good thing is, these two metrics can be calculated on any data. You don't need to understand the underlying distribution model at all. So the 50s or 90s, 97s, whatever we want, define normal behavior, but we don't need to understand the underlying distribution model. So every alerting system that forces you to use a certain distribution model actually makes the job much easier, and it doesn't need it. The only thing you need to know what is the range of normal behavior, which is the 15th percentile and the 97th percentile. Like in this case, what we see, again, this is the sample from before. We see that we have the median here, and we have the baseline calculated based on the median, and we see it's going to alert here, because that's the first time where we really see that the baseline is validated. If you remember before, we had alerts here, here, and here. Why? Because we were using the wrong underlying assumption of what our data is really like. Okay, now we know our metrics. We know we can work with the 50s and 97th percentile. We can use them for alerting by tracking them over time. But now we have to find that point where we say it's not going to be normal anymore. It would be a very naive assumption to assume that our 50s percentile over time always looks the same. It's never actually changing. The question is, how can we really figure out whether the change that we're seeing right now is within the range of normal or is not within the range of normal? The good thing is that we don't even have to solve this problem, because mathematically the only thing we're talking about is missed expectations. Mathematically, what you have to do to alert is you have to know how likely is it for a value that's usually 500 milliseconds with a given range to suddenly be 600 milliseconds, to suddenly be 700 milliseconds, and so forth. Again, we can do it for two scenarios. How likely is a certain error rate to occur or not, and for response times, is a certain increase in response time significant enough to trigger an incident or not? We have our error rate scenario here. So we have a typical error rate of 3% at 10,000 transactions per minute. During the night we have those 5 errors in 100 transactions. Should we alert or not? A lot of gut feeling going on here, but there's actually an answer to the problem. And the answer to the problem is in Vegas. It's not in Vegas because you can drunk there and just forget about your production system. It's about gambling, because statistics is everywhere. Like in this case here, how likely is it that these two dices, exactly the 4 and the 5 here, look like this? What's the likelihood of this? And there's a mathematical means to this, which is called the binomial distribution, which fortunately is one of the easiest distribution models that you could actually use. It just tells us how likely it is to see n successes in a certain number of trials. So how likely is it if you expect 500 milliseconds to see 5 out of 10 values to be higher, for example? So how many errors are okay? And we just put this into this binomial distribution model and have used a very sophisticated alerting tool that's called Microsoft Excel. So the likeliness, we have an 80% probability to see 5 or more errors, which is 2 times the standard deviation. So we do not need to alert. So we ask it, how likely is it in our scenario that we have here? Oops. 5 errors in 100 if our typical error rate is 3 in 10,000. How likely is this to occur? And it's a simple formula you put in there, so we do not alert. It's an 80% probability to see it. It's way beyond the 2 times standard deviations within which you would not alert. So how do we now translate this to response times? Response times are a bit more complicated than error rates. And we have this example here. We have response times of 300 milliseconds usually, and suddenly we measure all these guys down here. We have here 500 milliseconds, 400, 350, 350. So a lot of these are actually higher than what our median usually looks like. The answer to this problem is you use something that's called percentile drift detection. So you expect your percentiles to usually drift anyways. They never stay completely stable, as I mentioned before. If you measure your percentiles over time, even if you use the 50s or the 97s, they're going to change because your response times are just not super stable. But how much of this change for your response time is acceptable or not? So you can ask us, did this median now change significantly? We check all our values again, and this time we just highlight all those are above 300 milliseconds. 7 values are higher than the median. Is this normal? That's a simple question we now have to ask. And this is exactly the same problem we were looking at before with the error rates. How likely is it if your normal response time is 500 milliseconds to have 7 response times, values out of 10 that are higher than those 500 milliseconds? We again can use the binomial distribution. Isn't that great? A very simple model solving a completely different problem. If we apply the binomial distribution now, we see that we have a 50% likeliness to see values above the median. How likely is it to see 7 out of 10? The probability is 17%, which is, again, within our 2 times of normal distribution. Not an issue at all. So, now we're actually done. We're right on time, actually. We have defined which metrics to pick. So as long as you work with discrete metrics, it's fine. Once you move away from discrete, more discontinuous metrics, you usually don't think about a distribution model. Focus on the 15th and 97th percentile. These fit perfectly into like the bigger framework of distribution models. And you don't have to worry about them. How do you get the baseline? You actually just look exactly at those values and see how more likely they are to drift. How do you know that this happens? I think by now you should see it's not just about a value being high or 10 values being high or values being high for 2 or 3 minutes. There are loading systems out there that do it that way, but really calculating the likelihood of this. And yeah, obviously we have talked about calculating this value. Obviously this was just a very brief introduction to alerting and anomaly detection. There's way more things about statistics, probabilities, testing, and the things that you can look into. My goal today was use this 20-25 minutes just to give you an idea that normal distribution isn't out there, and there are very simple mathematical means to do it in a very reliable way that you can easily understand without having actually a PhD in mathematics. And the other goal was, if you have an alerting system, or if you even have a company that wants to charge a lot of money for investing in their alerting systems, ask them how they actually do their alerting. And if they come up with strange stuff like, okay, if it's for 5 minutes, even if you have those configuration options, if it's 5 minutes higher than what it used to be, kind of thing, really go away from it. There are sound mathematical stuff, and just to use my last minute here, when we discovered this, we all come from an engineering background. Wow, this is great stuff. We actually can get the Nobel Prize for this. That thing was, we hired a couple of math PhDs and says, yeah, that's basics, that's first semester mathematics. Still, it's very cool stuff. I hope I could give you an idea to look at alerting now a bit differently and what's actually the magic behind anomaly detection and alerting systems and what they actually do from their core principles. If you have any questions, get in touch with me, email, or via Twitter, and I'll post the slides tomorrow on my blog as well, so you can download them and I'll